So hello everyone. Let us now discuss the concept of compound cylinders. It is also called as composite cylinders, or it is also called as laminated cylinders. So compound cylinder or a composite cylinder or a laminated cylinder will function in such a way that there will be two cylinders at a time be functional. There is one is outer cylinder, one is the inner cylinder. You can see the same thing in this image. One is the outer cylinder and other one is the inner cylinder. Now when we are trying to use it, uh, when we are trying to use this concept of compound cylinder, we need to understand certain terms. So some of the terms that are generally adopted in compound cylinders are, so we for outer cylinder we have outer diameter as well as inner diameter, and for inner cylinder again we have outer diameter as well as inner diameter. So total 4 components will be there. So let us see some major important points in the compound cylinders. A compound cylinder is made by press fitting. So this concept I'll explain a bit later. Around an inner cylinder, the purpose is that the outer cylinder puts pressure on the outside of the inner cylinder. So what does this mean? The bore is put onto the compression. So bore means the outer part of the inner cylinder. So the concept is very simple. Inner cylinder will be put inside the outer cylinder. So when it is put onto the put inside the outer cylinder inner part will press the top part of the inner cylinder. That is what is called as press fitting. And let us see what will happen if the diameters are small or high in the upcoming slides. Now in a compound cylinder, the outer cylinder is having inner diameter smaller than the outer diameter of the inner cylinder. So this is the basic requirement in a compound cylinder for it to function well or for it to be properly designed, because these are one of the very important things in mechanical applications. So we need to take care of these basic things in a more cautious way. Because the inner cylinder is put inside the outer cylinder, the compression will act on the top surface of the inner cylinder. Okay, so the next point is the inner cylinder is shrink fit to the outer cylinder. Earlier, what did we learn? Outer cylinder puts pressure on the outside of the inner cylinder. Now, what is happening? Inner cylinder is shrink fit to the outer cylinder. So, what will happen here when they are trying to fabricate this compound cylinder? First, they will heat it to some temperature. After heating it to some extent, they'll try to cool it down. Once if it is cooled down, what they'll do, they will check the contact pressure. So the contact pressure is a place where both cylinders are acting together. So there will be one junction between inner cylinder and outer cylinder. That specific junction, we'll see a contact pressure being developed. So once if you see this contact pressure at the two junctions of the cylinder, we need to design both the cylinders in such a way that it will take the required pressure. Next, let us go to the next slide. Yeah, next part is the compound cylinder basic fundamental understanding. What it does, the cylinder, it will introduce compressive stress at the inner cylinder. So what it does, it introduces the compressive stress in the inner cylinder and tensile stresses in the outer cylinder. So this is very important. Compressive stress at inner cylinder and tensile stress at the outer cylinder. Then inner cylinder is subjected to external pressure because we'll pour fluid into it, and outer cylinder is subjected to internal pressure. So you can see this image also. We have the internal cylinder, we have the outer cylinder or external cylinder, and the corresponding radius. So radius of external cylinder, radius of internal cylinder, and radius of the junction. So initially, if you see, this is the only outer part. This entire section is only outer part, and this section is only internal part, and this is the junction. So combination of junction here. Then we have the corresponding pressures also. So if someone wanted to see how exactly the pressures would look like, so this is how the pressures would they look like. So if you have the outer cylinder and inner cylinder, see the stress distributions depending upon the pressure being inserted into the cylinder. So there are two cases, rather three cases. First, initial stress without any fluid, and then some fluid will be poured into the cylinder. That is the stress due to fluid. And the final stress is initial stress plus stress due to fluid, which means total stress is equal to stress without fluid plus stress with fluid. So what are all the stresses that we need to calculate? Sigma C and then sigma R, that is circumferential, radial and longitudinal. Longitudinal stress anyways, we know that it is constant throughout the section. And if you see the stress distribution parts, we have for initial stresses without fluid. So without fluid, the case that we are going to consider here is the outer cylinder is undergoing tension because the inner cylinder is placed inside and the outer cylinder is touching the inner cylinder, it will undergo compression. So inner cylinder will undergo compression. And then we are pouring some fluid. So if you are pouring fluid, what will happen? The fluid inside the inner cylinder will ensure that the inner cylinder also will be subjected to tension. So both of them will be subjected to tension, inner as well as outer. And then the final stresses. In final stresses, what will happen? So the compression part of the inner cylinder without fluid will dominate, will be less than the tension part of the inner cylinder with fluid. So therefore, in final stresses, we will have two tensile stresses developed at a portion of outer cylinder as well as inner cylinder. Next. Yeah. So this is a very, very important concept. I have shown one demonstration also in the next slide. You can watch it. Here, there are three cases for a cylinder to fail. One is the ideal case. One is the ideal case. Second one is the worst case for loose fit. And then we have the worst case for tight fit. So these three cases should be normally considered for our analysis. Ideal case, worst case for loose fit, and worst case for tight fit. So here, let us see the conventions first. We have, see, don't forget about all these things. This is not required. That is not required for our understanding as of now. So we have diametrical interference. This is called the junction, where inner as well as outer cylinders will meet at a point. So this is called junction. And we have inner body, outside diameter, outer body, inside diameter. Like that, we have it for all these three cases. So let us understand what are all these three cases. One is ideal case, worst case due to loose fit, worst case due to tight fit. So I will demonstrate it with an example here using an animation. So here I have considered 4 glasses. So this is glass 1, glass 2, glass 3 and glass 4. So these 2 glasses are looking like same, but the diameters are a bit different. And this diameter is different from less than these 2 diameters, and this is the least diameter one. So this is the maximum diameter, this is the minimum diameter. So let us see what I'm doing here. So first, by considering these 4 glasses, I'm trying to put one glass into the other. So you can see there, I'm trying to demonstrate these 3 worst cases. This is the worst case that I'm showing right now. So what's happening here? That both the cylinders are not going inside too much. The fitting is not good, which means the inner cylinder, this is the outer cylinder, inner cylinder is not going into the outer cylinder. So that's not a good case. That means tight fit. Then we have the other case where I'm trying to put the best fit. So this is the best combination where you can see inner cylinder is almost going into the outer cylinder, and this is what is desired for any design. So this is the best case. So then, and it is also not falling down. That's what we require. And then we have the loose fit. See what's happening in the loose fit. Whenever we have used the loose fit, the inner cylinder is coming out of external cylinder, and that is also not ideal solution for a proper design. So by understanding these 3 phenomena, you might have understood that what is the best fit, what is the worst fit, and what is an ideal fit. Of course, best in terms of tight fit. tight fit, loose fit, and ideal fit. Okay, let us go to next slide. Okay, so when you take these compound cylinders, so the solution is categorized into three categories, three separate effects. One is shrinkage pressure only on the inside cylinder. So now what is happening? The cylinders are shrinking. So if the cylinders are shrinking or reducing the dimensions because of the heating, cooling process, outer cylinder is touching the inner cylinder. In all these cases, there are three possibilities. One is shrinkage pressure only on the inside cylinder, and we have shrinkage pressure only on the outside cylinder, and internal pressure only on the complete cylinder. So three cases. So these three cases, let us understand using these three figures in the coming slides. Okay, next. So now let us take the derivation of it. How do we derive the stresses? So having understood the basic phenomena behind what's happening in a compound cylinder, let us try to derive the expressions for all the three stress parameters in a compound cylinder. So this is the compound cylinder that was adopted. So R1 is the inner cylinder or inner tube radius. R2 is the junction radius. So this is the junction radius. And R3 is the outer diameter radius. So outer tube radius. So having seen all these three things, now we need to calculate the initial stresses. As we discussed, we have three parameters: initial stress, stress after inserting the fluid, and final stresses. So in the initial stress, we have let R2 be the radius at common surface, that is the junction. So this is the common surface. And then P is the shrinkage pressure. And now let us try to derive the expression for inner stress for inner tube as well as outer tube. So now if you take the inner tube, so inner tube is this. And for this inner tube, you have inner radius R1 and outer radius R2. Because this outer radius is R2 as it is the junction part. Now we know that Lamb's equations are given by this expression, both radial as well as circumferential. Now when you apply the boundary conditions, so at R is equal to R1, sigma R is equal to 0. So there is no stress at all. So there is no stress at all at internal radius. So therefore sigma R is equal to 0. But at R is equal to R2, that is at the junction, because both are touching each other, some amount of pressure will be generated. So that is P. So therefore, by substituting these boundary conditions into these, we will get these two expressions. Then for outer tube also, we have inner radius. So for outer tube, inner radius is R2 and outer radius is R3. That is the maximum part. So again, so here for our better understanding, B, A are for inner radius or inner tube, and B dash and A dash are for outer tube. So now again, by applying boundary conditions, at the extreme end, R is equal to R3, that is outside diameter, no pressure, 0. But again at junction, because both are touching at each other, the pressure is P. So therefore, we got these expressions. Now the four constants can be found out from equations 1 to 4. These four, with these expressions, we will get the constants. Next, moving forward, now stress due to fluid pressure. Now this is the second case. So we have calculated initial stress, now fluid pressure. So so now what will happen when the fluid is inserted into the cylinder? When the fluid is inserted into the cylinder, what will happen? Both joints are there. What is the joint there? A junction where both outer and inner cylinder are touching each other. Now when the fluid is admitted, intensity of the pressure is resisted jointly, because now the fluid will go to internal cylinder. Once the fluid goes to internal cylinder, it starts functioning and joint will play a role. So in that scenario, again we take these Lamb's constants, and then we have at R is equal to R1. So what is R1? This is inner tube. So at inner tube, we have fluid. So because we have fluid, the pressure at that point is equal to P1. And at R is equal to R3, external. So do we have any pressure there? 0. Only internal cylinder is there. That is not the pressure due to fluid. So that is equal to 0. 0. So now the constants again can be calculated. Now what we will obtain? we will obtain the value of circumferential stress due to fluid pressure, right? And the final stresses are initial stress without fluid plus stresses with fluid. That ends the basic understanding of how to derive the expressions for compound cylinder stresses, radial stresses and circumferential stresses. I'll end this lecture with a small problem. So a compound cylinder is made by shrinking one tube to the another, and it is subjected to an internal pressure of 90. So before the fluid is admitted, so that is the initial case. Internal and external diameters of the compound cylinder are 180 and 300. Internal and external are 180 and 300. And the diameter at the junction is 240. So what we are given with? We are given with R1, R2 and R3. After shrinking, radial pressure is given 12 meganewton per meter square. We need to calculate the final stresses developed on the compound cylinder. So let us see step by step how to calculate this problem. Fine. So now, first step, internal pressure in the cylinder. So it is given as 90. So 90 meganewton per meter square. Internal radius is 180 by 2, and then that is 0.09 meters. And we have external radius, that is R3. So don't get confused here. R1 is internal, R3 is external. In between is R2. Okay. So R3 is given as 300 by 2, 0.15 meters. And R2 is given as 120 mm or 0.12 meters. Now what was given? Radial pressure at the common surface after shrinking. So that was given as 12 meganewton per meter square when after shrinking. Okay. Right. Now what do we need to calculate? Final stresses. So what are the steps that we need to follow? Calculate the initial stresses for internal tube and external tube, and then calculate the stresses due to fluid pressure, and then calculate the final stresses. Okay. So final stresses that are developed would look like this: sigma R, sigma C for inner tube as well as outer tube. Okay. Fine. Next. Before the fluid is admitted, inner tube. So there is no fluid now. What will happen at R is equal to R1? Sigma R is 0. Again, remember that if the fluid is not present inside the cylinder, then the pressure will be there only at the junction. And at inner and outer, it will be 0. And then at R is equal to R2. This is at junction. So at junction, you have the stress. How much it is given as? It is given as common surface 12 meganewton per meter square. So once if we substitute these, we will get the constants of B and A. Those are all Lamb's constants. Fine. Next, after this, the circumferential stress at any point in the inner tube is given by sigma C is equal to, again, Lamb's equation. We are substituting the values. And here we have written the minus sign, which represents that the entire stress is compressive. That's what the understanding we need to get. Now, at R is equal to R1, that is 0.09 meters, we are trying to calculate the circumferential stress at two different radius here. R is equal to 0.09 and R is equal to 0.12 at two different radius. That is at inner radius as well as outer radius, at the junction. So the circumferential stress for inner cylinder is 54.82, and most important thing is compressive. And the circumferential stress at the junction is 42.82. It is also compressive. Remember these values. We have to use these values for final calculation. Next, like inner tube, we have outer tube. Here also, for outer tube, at R is equal to 0.15, that is at the outer part, there will be no stress. And at R is equal to 0.12, this is the junction, stress will be there. So again, we will get the constant values B dash and A dash. Again, we need to calculate the circumferential stress, but here at what point? At the junction. Now here it is tensile. At outer tube, when you are calculating the circumferential stress, it is tensile here. And what is the other stress we need to calculate? At R is equal to 0.15. That is at the outermost part. So that the circumferential stress for the outer tube will be 42.66, and it is also tensile in nature. Fine. Next. Now, fluid is inserted. fluid is inserted into the inner cylinder. Again, same equation, radial stress. Now, but what is the radius to be considered? Where we need to consider this? At a portion where fluid is inserted or admitted. So where are we pouring the fluid? Into the inner cylinder. So at the inner cylinder, we are pouring the fluid. So at radius 0.09, and we know that sigma r is equal to 90 meganewton per meter square. So we know sigma r. We need to calculate, we need to write the expression in terms of B minus A. Fine, B and A. And then at r is equal to 0.15 meters, that is outer, we have understood that there is no fluid there. Therefore, the stress is 0. The radial stress is 0. So now we will get, by solving the equations 90 and this, we will get the values of B and A. So once if we get the values of B and A using radial stress, what do we need to do? We need to calculate the circumferential stress when fluid is inside the internal tube. So in this again, at r is equal to 0.09, that is at internal tube, circumferential stress. And at junction, this is the circumferential stress. And at the outermost part, 101.23 is the circumferential stress. All three are tensile in nature. Now, so the final circumferential stresses are given at different points and they are calculated as follows. So the convention is tensile stress is positive and compressive stress is negative. So let us see here. In inner tube, we have two cases, correct, right? One is internal radius, that is 0.09, and junction radius 0.12. At this part, these are the values that we have already obtained in the previous steps. Compression is negative, tensile is positive. So initial stresses in the inner tube are these two, and 54.82 and 42.82 compression. And for outer tube, initial stresses are these. This is from step A. Now, when the fluid is inserted, again we have calculated the stresses. This is from step B. Now, the total stresses are sum of initial stress plus, so this plus this. So these two should be added. So then we will get the values of final stresses as written here. So in inner tube, circumferential stress and both are tensile in nature. One important thing is we need to calculate these stresses at all the portions. This is the inner diameter, this is the junction for inner tube, and for outer tube, this is the junction and this is the outer diameter. So this is how we need to calculate the circumferential stresses for a compound cylinder. This is one of the very important problem for the exams also. One more thing I will highlight here, I'll just revise briefly. So compound cylinder is the combination of two cylinders. Smaller diameter cylinder will fit inside the larger diameter cylinder. Because of that, there will be four components: internal diameter and external diameter for outer cylinder, and internal diameter and external diameter for inner cylinder. So now, because the outer cylinder is sitting on the top of inner cylinder, that will undergo compression. And if there is no fluid inside the inner cylinder, only pressure will be acting at the junction. But if we have the pressure inside the inner cylinder, so pressure should be considered in the inner cylinder, but always the pressure at the outer cylinder, unless otherwise in special cases, it is 0. Because of that, we always make use of Lamb's equations and Lamb's constants. So Lamb's equations and Lamb's constants. So in Lamb's equations and Lamb's constants, we always use radial stress as a parameter. We apply the boundary conditions, get the values of A and B, and A dash and B dash. A and B are for inner tube, A dash and B dash are for outer tube. Once we obtain those values, we'll try to calculate the circumferential stresses without fluid and with the fluid at all the portions, at inner tube, at the junction, and at the outer tube. So with that understanding, we will continue in the next lecture on how to calculate the differences in the radius because of the shrinkage, and how to design a thick cylinder using failure theories. Thank you.